All right, so let's take a look at this spell work problem. You have $5,000 in an account earning 4% interest compounded continuously. What do we think of first thing right away when we see this sentence? What should be our very first noticing thing? How do we build this equation? A very important word right here. These two words are super duper important. Because what does compounded continuously tell us? That compounded continuously tells us we're going to use the PERT. This equation. So whenever we see continuously compounded or compounded continuously, those two words together means we're going to use this guy here. What pieces do we know? It starts at 5,000. So which letter in our equation is the 5,000? It's going to be the P, yeah. So our 5,000, that's the P. Oh, yeah, I'm just going to go. Boom, as a highlighter. So in this part here, we've got our 5,000. E is a number, so it's a button on our calculator, so we have the E. What is our rate? The 4%, which we write as a decimal, as our 0.04. And at this point, before we read the word below, the sentence below, we do not have a time. We still have two variables here. This is we don't know what our bank account is, and we don't know what the time is. So this is kind of our basic form of the equation that we're going to use for both questions. These are two different questions using this equation. So the first one is very much last chapter vibes. How much money will we have in 10 years? What are we going to do with the 10? Put it in for the T. So this 10 goes in as T. So we're going to figure out the amount in our account with our 5,000 e to the 0.04 times 10. That T. And that's something we just type in the calculator. So I'll put it up on the screen here in just a second. I just got to write it down so that I don't lose track of it. Oh, that's right. I forgot I'm on this version of the screen. Different setting. So it's still written right there. So we've got our 5,000. To get the E, we hit the green button, and then we hit our LN because they're so linked together. I know I've got a whole bunch of stuff in the way, but oh well. 0.04 times 10. And you can straight up type it in exactly as it is. And it's going to spit out, if you look at the tiny computer, the tiny screen, it's a little easier to read. Our $7,459.12. Close our calculator then, because now I have to not do it that way. There we go. So if we put this money into an account and do not touch it for 10 years, we will have that the amount in our account is $7,459.12. So free almost $2,500 just by letting the bank hold on to the money for us. So this is the exact way we did it last chapter. Same vibe. Part B is this chapter stuff. What do we need to do to double the money in our savings account? So we're going back to the original equation. How are we going to set it up?
500 times 2, which is 10,000 equals 5,000.
I totally know what you meant. We're good.
5,000.
Boop. Yeah, we want to know how long until our money doubles. So we took the money we started with and we doubled it. You can do it as two pieces like this, or you can multiply them together and put it as 10,000. 100%, both ways are totally valid. Honestly, doing it like this makes it a little easier calculation-wise, because what is our first step going to be trying to get t by itself over here?
Dividing by 5.
Ah! There we go. Yep, our first step needs to be to divide by 10,000. 5,000. See, I did the exact same thing. If we divide both sides by 5,000, this guy and that guy cancel out. That's the whole point of doing that. And then if we don't multiply those together, I can just cancel out over here as well. You don't have to do it that way, but it totally works. So we get that 2 equals e to the 0.04 t. And I know they're a little smudgy, but I'm giving us a little space. I got it. What should we do next? Put it into log form. What's our base? Here. E. So if we need to make a stop at log base E, totally valid. If we can go straight to ln, also totally valid. So I'm going to make a pit stop into log base E over here just to run out of space. So log base E of, what's our argument? 2. And it's going to equal that power, that 0.04 t. Well, this is the exact same thing as if we had ln of 2. Log base E is the same thing as ln of 2. ln is a button on our calculator, so that's one of the reasons we love her. Because that's something we can type in on the calculator, and we don't have to do a gosh darn thing otherwise to change that base. We have one last step on here before we get to type it in the calculator. What do I need to do to get my t by itself? Divide by 0.04. We got to get the t by itself, so I need to divide by a 0.04. I give myself a little bit more space over here. So we get this exact answer that t equals ln of 2 over 0.04, which is all well and good, but that has not a dang on clue as to how much time that is. So to figure out how much time that actually is, we're going to type the sucker in a calculator. And again, I'm going to put the calculator up. I know all the letters are going to be in front of it still. It's just because the computer's a grumpy guess. So we're going to have our fraction that has our ln of 2 over our 0.04. This is the most chaotic screen I think I've ever showed y'all. Holy cow. Oh my gosh. So we get 17.3. If you look on the teeny calculator, it's a little easier to see. And in fact, I can erase that there right now.
Would you round it up to 33, or are we going to the tens place?
Let's just go with the tenths place.
Okay.
So we'll do 17.3. That is not the button I meant. So every single piece of writing that I just had up here is now gone. Love that so much for us.
Is there not an undo button?
No. It's one of the reasons I don't typically do it like that, but that's where it is. So we had our ln of 2 over 0.04. This was our answer here. And that is approximately equal to our, now I've totally forgotten what it is, 17.3?
Mm-hmm.
That's what happens when I try and do things the shortcut way and not import things properly into the software. So, that's what we're looking at when we're trying to figure out the how long till it doubles, how long till it triples, how long till I have X amount of money. We put that as the A piece in these continually compounded bits, and we go from there. Questions on either of these two? Hopefully we were writing quickly because I did not give us warning that they are about to disappear. Fun times. Okay. So we have a chapter test coming up tomorrow. Yes. So I have the review here. Anything we want to work through? Number three. Where it says to evaluate without a calculator. Now, I'm saying, we are going to be allowed to use calculators. I'm not going to at any point take the calculators away. I just wanted us to try. All of these can be done without a calculator. If you're 100% stuck, calculate away. But all of these can be done without a calculator. Every single one of these could be a power that we know. So that's what we're thinking about here. Think about our, whoa, way too chunky of a pen. Hold on a second, let me fix that setting. This is when we're going to think about our BP equals A, that we can switch with our log BAP, log base B of A equals P. This is a very important piece of this chapter. We've got to know this thing. You got to know it. It comes up so frequently. So with all of these ones in number 3, we can do it using just these tools. So for part A here, we have a log base 9 of 1 over 81, and we're trying to figure out what it equals. So we're trying to figure out P. So we have a B base of 9. So we want to know 9 to what power equals this argument, that A of 1 over 81. How do we make something flip into a fraction like that? What would a power need to do to make something flip? Negative. It would need to be negative. So we know our power is going to be negative. What relationship does 9 have to 81? 9 to what power equals 81? 2. 9 squared is 81, and 9 to a negative power makes a fraction. So if we combine them together, 9 to the power of minus 2, we get 1 over 81. So that's one of the ways to kind of logic your way through this. The other way is to kind of type it in the calculator and do it as a guess and check style. And what I mean by that is if we go to a calculator where it's going to work properly for us, and I just start playing around. So maybe 9 to the first. I'm going, well, that's definitely not it. If I go 9 to the second, oh, that's getting bigger, so I need to go smaller. 9 to the 0. It's smaller, but not small enough. 9 to the minus 1, we get 1/9. I'm headed in the right direction. So you can kind of guess and check your way into this. 9 to the power of minus 2. It's a fine way to do it. Ideally we could do it without having to do it as a guess and check, but totally works. This also will still work if you do it using our change of base, where we would set that up as log of our argument over log of our base. So if you type it in the calculator like this, and I know that's super smudgy, but I'm trying to make things visible when we zoom out. If you type it in like that, you should get the exact same answer. You guys can do it with log, or you can do it with ln.
I don't understand
D. ln of E. So think about ln of E, meaning log base E. So this is the exact same thing as if we had log base E of E. And we want to know what this equals. So again, switch it around. Our base is E. We're trying to figure out the power that gets us to E. What power would E need to have to be itself? 1. Whenever the base and the argument are the same, the power is 1. And you can do that in the calculator as well. You have to be a little tricksy with it because we can do our ln of e. To get e, we go second e. It's going to put us up in the exponent, so we just kind of got to hit 1. That's kind of our default power. So we have to put something there. That is not... I meant to close the parentheses there. There we go. Still gives us the same thing. ln of e to the first is 1. So you can use the calculator on it, or we can switch it around like this. Same thing with e, is it's kind of doing a weird here. Because we have a base of 7, we're trying to figure out our power that gets us to 1. What exponent will make 7 turn into a 1? Anything raised to a 0 power is 1. So log base 7 of 1 equals 0. In fact, any log that has an argument of 1 will have a power of 0. So we could look at c as well. It does the exact same thing. It also has a power of 0 because it has an argument of 1. So you can do these with our change of base formula. You can do these by switching these from our log BAP to BPA. Both are valid techniques. It's just important to be able to practice them. These ones you don't have to use a calculator. When it comes time for the test, if you use a calculator and do change of base, totally fine. I just wanted you to practice doing it both ways on the paper. Because I mean like that. Wahahaha. What other questions do you guys want to go through on here? 2a. Yes. Expanding. 2a. You were looking at 4. Yep. We can look at 4 next if we want to. But we're going to do some expanding. What do we do first when we're expanding? What's our first step going to be? Because we're trying to make this have as many logs as possible. So I want to split this guy up because that 2x to the 4th over y to the 5th is gross. This is that thing where we take our division and it's going to become subtraction. Our multiplication becomes what? Addition, adding. And our powers are going to come down and become constants or coefficients. So these are the kind of orders we go through. My division symbol looks weird. There we go. When we are condensing, it's just the exact same things in the opposite direction. So instead of going top down, left to right, we'd go bottom up and right to the left. So expanding goes this way, condensing goes that way. So our first step is going to be to take any division in here and make it turn into subtraction. So I see division right here. So when we write this as our first step in our expanding, when our division becomes subtraction, we're going to have our log base 4 of our numerator, so the top bit, 2x to the 4th, and we're going to subtract the denominator. And it gets its own log, log base 4 of y to the 5th. So our division turned into subtraction between the numerator and the denominator. So that's this step done. Our next step is that any multiplication becomes addition. Where do we have multiplication on this one? The log 4 doesn't count as multiplication. It's its own operation. We do have a piece of multiplication here. Between what two pieces? Look in the green bits. Where do I have two things? The 2 and the x to the 4th. Right here. This is where we need to take our multiplication and have it turn into addition. Thank you, dear. So these are the guys we're going to split apart with our addition, or our multiplication becoming addition. So again, every time I'm expanding, every time we split it apart, I need to get a new log. So we're going to have our log base 4 of 2 plus our log base 4 of x to the 4th, and then our minus log base 4. This guy's still just chilling. Y to the 5th, just chilling with us. So that's how we take our multiplication and turn it into addition. Our last piece here is that our powers become coefficient. What powers do we have? Close. Is the 2 a power? Just the 4 and the 5. So the 4 is an exponent, the powers come down, and it's going to become a coefficient in front of this guy. My 5 is going to come down and be a coefficient in front of this guy. So our final answer on this is going to look like log base 4 of 2 plus, we're going to have our 4 log base 4 of x, and then we're going to subtract our 5 log base 4 of y. We know we are done expanding when after each log is just one thing. So I have log base 4 of 2, log base 4 of x, log base 4 of y. I have one piece after each log. I can have as many logs as we need, but I just need one thing after. So this is our fully expanded answer. This is our guy right here. What's up? Yeah. So let's do one that's like the exact opposite of that, where we're going to condense it back down. So just so we can practice both things. So let's look at 4a. So we follow these same steps. We're still going to use this same laser pointer. There it is. This same kind of structure here, where we're going to take our pieces. Oh, let me do my little check mark so we can follow the color coding. Boop. That one was done badly in pink. There we go. That one was done in pink. We're going to take those same steps. We're going to have our division and subtraction that are linked, our multiplication and addition that are linked, our powers and our coefficients that are linked. Just when we're condensing and we're making it smaller, we just kind of go in the opposite direction. So our first step, instead of being that our subtraction becomes division, we're going to take our coefficients and make them powers. Then we're going to take our addition and make it be multiplication. And then our last step is that our subtraction will become division. So it's very, very much the same process, just flipped. I'm trying to make them so they're same readable. So it's the same pieces that are linked together. It's just we're going the other direction. So for 4a, we're starting with our coefficients becoming powers. So what pieces are going to move for this first step here, where coefficients become powers? The 5 and the 7. So the 5 is going to go up and be a power on the x. The 7 is going to go up and be a power on the y. So our first step when we're rewriting this is going to be to have our log base 2 of x to the 5th plus our log, there we go, log base 2 of w to the 7th. So the multipliers out in front, those coefficients, go up and become powers. Our next piece that we do, our addition becomes multiplication. I do have addition in here. I have this plus right in the middle. So what that means we're going to do, just like in the last one where we took our 2 separate pieces and we split them out to make more logs, now I'm trying to get everything back into one log. So I'm going to take my 2 arguments and multiply them together. When we condense, we should be losing logs. Our goal at the end is to wind up with just one log that we write. So we're going to have our log base 2, and we're going to take our x to the 5th times w to the 7th. We do not have any subtraction, so I don't need to do anything with this guy. We have just one single term after a log, and we're down to just one log. So this is my answer. Not like the color of that hard. That's way too bright. There we go. So that's our fully condensed answer. We're down to one log. There's just one set of terms after it. Okay? What else you guys want to do? Number 8. Let's look at that one. Identifying some transformations. Boop. All right, so we've got that the graph of a logarithmic function has a base of 7, a stretch of 5, an asymptote at x equals 3, and has been shifted up 8. So if we think about our logarithms and their graphs, that's when we had our transformation form, which has our a log base b of x minus h plus k. That's our transformation form. We use that when we're graphing. We use that when we are doing these kind of transformation pieces. So what pieces in this sentence are going to match up with something up here? What do we have? The base is 7. So base of 7, that's the b. What else do we have? Because it's been shifted up 8. That's our vertical shift. Yes, k is going to be our 8. What is our h going to be? Does h do my stretch? What does h do? It's going to be the 3. It's our horizontal shift. It's where our asymptote is. It's done our horizontal shift, which means where's the 5 going to be? Not x. A. That's our vertical stretch. So think about our ya plus k. That's where our a, h, and k go. Our x plus h, our ya plus k. Those are the guys. B is where our parent function comes from. So substituting these pieces in, we're going to have our 5 that's in the front. Log base 7. X minus our h, which we said was 3, which is going to scooch it to the right 3, plus our vertical shift of k. So this thing is going to scooch up 5. So we have a stretch, a shift right, and a shift, up 8. I'd be like, I didn't think we had 2 5s in here. My brain got stuck. That's trash. Plus 8. There we go. Because we got shifted up 8. Okay. Say it in. Let's look at 11 real quick. So 11 is very much like what we did in the bell work, except we give you the equation, so we don't have to think about it. So we have that f of t, that's the amount we have left. So the amount of this titanium 44. Titanium 44 is its name. There's nothing special about that 44. Whenever they have that piece in there, that's them trying to trick you. Titanium 44 is its name, just like if I was Mrs. B number 4. It's just part of the name, which I believe technically I am Mrs. B number 4 at the school, in the math department specifically. So this is the amount of titanium we have left. And if it helps you to switch it to be a capital A, totally fine. The little a is the amount we start with. Then we have our E, which is a number on the calculator, minus 0.011 to the T. That's our time. So the question says, to the nearest 3 decimal places, after how much time, so our question is about time, so T is going to be our variable left. That's our goal. Will we have 50 pounds if we started with 100 pounds? So this 50 pounds, is that going to go in the capital A total or the little a what we started with? The capital A total. So the amount, that's our F of T, the amount we have left. So I can write this as our 50 equals, how much did we begin with?
100.
The 100. That's going to go in for the little a, our 100 pounds. So if it helps to get it out of that F of T notation, that's totally fine. If you want to leave it as the F of T, that's totally fine too. But this would be how we kind of set that up. And my goodness, do those blue and purples look really similar up there. Those are 2 different colors.
They don't look similar.
Oh, from this angle, they look practically identical, the blue and the purple. So I'm just gonna... All right. So what are we going to do to try and solve this?
Divide by 100.
Divide by 100. That's got to be our first step. I'm trying to get T by itself, so I'm going to divide both sides by 100. And you can write this part as a fraction, or you can do it as a decimal, because 50 over 100, we're going to get 1/2, or you can put 0.5. Either way is fine. But that's going to give us e to the minus 0.011 t. Because we canceled out our 100 here. That's the whole point of dividing by the 100. What can we do next?
Is it okay that I was using the decimal 0.5?
Absolutely valid.
My brain likes that better.
Absolutely valid. You can absolutely do that as 0.5.
Well, next we turn it into log form.
Put it in log form. What will this be in log form? ln of 0.5 or 1/2. Again, I do not care. Equals our power. Negative 0.011 t. Fixing that negative because that looked weird. So now we're 100% into kind of what we did in the bell work. What do we do to get t by itself? One last step here.
Divide by negative 0.011.
And this would be an exact answer. It's gross, but it is an answer. I could write that my t has to be ln of 0.5 or as 1/2. I genuinely do not care how you put it. It's the same exact thing. Negative 0.011. I have an answer. Yay! I know what t is. Huzzah! How many years is that?
63.013.
We need to type this into our calculator to get our decimal answer. I'm going to put that on my calculator. And we can type this into our fraction, second column, third button down. And you can put in our ln. You can put in the 0.5 over our negative 0.011. Or you could put in our ln of 1/2. Totally valid over our negative 0.011. We will get exactly the same answer. It is 100% exactly the same. So 63.013, because they do tell us 3 decimal places. So this is our answer. Down here. There we go. 63.013 years. Okay. we are just about to get interrupted with the announcement bell. So keep working on this. The answer key should be posted for it. So work on things. Let me know if you guys have questions on stuff. Feel free to send me messages or come to my support hours today during fifth period. You can come during any lunch period. Yep. All right, you pass. And then I'm going